This is an introduction to vectors. I'm going to go over the motivation, where they come from, what their basic properties are, how to write vectors in component forms, and what unit vectors are. Vectors are a model of force. So what that means is we go out in the real world and we push on things and pull on them, and we see how objects respond to having a force applied to them. And then in our mind, we have a little model, a copy of the real world. And however we observed the real world behaving, we use those as abstract rules for how our model must behave. So what makes one force different from another force? Well, if you're pushing in a different direction, that's a different force. And if you're pushing harder or softer, that makes it a different force. What doesn't matter is the location of the force. If I am pushing on a box in Kansas, or I'm pushing on a box in California, it doesn't matter. If I'm pushing in the same direction with the same amount of force, those are the same forces. It doesn't matter where they are. We represent forces with arrows, and I call the beginning part of the arrow the initial point, and then where the arrow stops, the terminal point. So if this is P and this is Q, then I would denote this vector right here, PQ, and then you draw a little arrow over the top of it. Vectors are in standard position when the initial point is at the origin. So if this vector, if the initial point was not at the origin, let's say it was like up here somewhere, then what I would have to do to put it in standard position is first I would have to slide it down like that. So, if it was like up here, what I need to do to slide it down is I would have to subtract off whatever the initial height was. And then I would have to slide it over there to get it in standard position. So when you do this formula, terminal minus initial, what you're doing is you're really taking the vector that's just like floating around out there in space, and you're sliding it down and sliding it over. That is a legal move because it doesn't matter what the location of the vector is. All that matters is, you see, I haven't changed the direction of the vector, and also I haven't changed the length of the line. This may be breaking it down more simple than a Calc 3 student needs, but let's do an example of this. So I've given us 2 points, and we're asked to write the vector that connects these points in standard position. So what I'm just going to do is final minus initial. So here 0 minus 2 is -2, 5 minus 3 is 2, and then -1 minus 1 is 0. So when you write a vector in standard position, a lot of times we put these kind of pointy brackets around the edge of them, just to denote that we're talking about a vector and not a point. And when we do this, we say that the vector is in component form. So what can we do with vectors? Well, we can perform vector operations on them. So again, this is borrowed from the way reality works. So what can you do with forces? Well, you can make a force stronger or not as strong. So if I have a vector v here, and all I've done is, I haven't changed the direction. All I've done is push in the same direction. Is that the same direction? Push in the same direction. But now I've tried to draw it as twice as long. Then this vector is going to be 2v. Okay, so that's a force in the same direction, but twice as hard. And then also maybe right here, maybe if I draw it just like half as long, then that would be like 1/2 v. Okay, and then one more thing that I want to point out here is, if you have the same vector as the original vector, except it's going in the other direction, that makes it -v. Okay, so those are the different ways that you can rescale vectors. You can also add vectors. What this represents in the real world is more than one force being applied to an object. So the way this works is you take any one of the vectors, either one, and I'm going to add these two together. Then what you do is you take the the vector and you slide it up there so that the initial point of one of the vectors sits right on the terminal point of the other one of the vectors. So this is the same vector as v, because remember, it doesn't matter where they are. I haven't changed the direction and I haven't changed the length, so those two v's are the same v. And then now you connect the initial point of one of the vectors to the terminal point of the vector that you moved. And that red vector right here is u plus v. So this red vector right there, sometimes people will even call it the resultant vector, is u plus v. So that right there is u plus v. And that's what happens in the real world if you have more than one force being applied to an object. Okay, also we can measure the magnitude of a vector. So this is a number that represents how hard you're pushing on something. So here I have a vector v written in standard position. So that means this vector starts at the origin and goes out to the point x, y, z. So it starts here and then it goes out like this. And this right here is x, y, z. And what we want to do is measure the length of that line. And the way that we write that is we put absolute value bars around it. Sometimes you'll even see in books, they'll put the double absolute value bars, because it's not really the same thing as absolute value. We're measuring the length of a line. So, I mean, in some very general sense, they are the same thing, but one really applies to vectors. So I don't know. I don't want to get too lost in the notation, but this is the way we write it. We put bars around it. And it's just the Pythagorean theorem. That's how you measure the distance from the origin to a point. So x squared plus y squared plus z squared. We can also measure the direction that a vector is pointing in. We call these direction vectors or unit vectors. Unit is the word in math that means one. So if you ever see somebody say that it is a direction vector, or if you're asked to find a unit vector, what that means is you're looking for a vector whose magnitude is 1. I'm going to just go ahead and put a star around this definition, because my experience has been that it's a very simple definition, and it is just really slippery. It just is so easy for that to go out of students' minds. You're going to be like, makes perfect sense now, but then 5 minutes from now, you're going to run into somebody and they're going to be like, hey, what's a unit vector? And you're going to be like, I have no idea. So I don't know what to tell you. A unit vector has magnitude 1. That's what it means. Please remember that. Okay, so that's the way the kind of geometry of it works, but that still doesn't tell us how to like get the answer as a number. So good news. It's really easy. Basically, you just add the x's together and you add the y's together and you add the z's together. So I have two vectors here, u and v, and I'm going to calculate the sum of these two vectors. So 2 plus negative 1 is 1. See what I'm doing here? And then negative 4 plus 5, that's also 1. And then 7 plus 3, that's 10. So that's it. That's how you add two vectors together. For another example, let's just find here, let's say 3v. So this really does just work exactly the way that you would want it to work. The way that you rescale a vector is, if you want it to be 3 times as long, you just multiply all the coordinates by 3, and then they're all 3 times as big, and then it makes the length 3 times as long. So 3v here is equal to, I did v, so 6, negative 12, 21. So the algebra of vectors is really easy, so that's kind of nice. Okay, I can pretty much guarantee that this question is going to appear on any test that you take that has vectors on it. This process is just fundamental to using vectors. So I give us a vector and we're asked to find a unit vector in the same direction. So what we need, remember, so what's a unit vector? It has magnitude 1. So I'm going to start off by finding the magnitude of the vector v. Okay. So I'm just going to use the formula for the magnitude. So this is going to be the square root of negative 2 squared plus 1 squared plus 2 squared. So this is going to be 4 plus 4 is 8 plus 1 is 9. So this is the square root of 9, which is 3. So this vector that I've given us here is a vector, and the magnitude of the vector is 3. But I want it to have magnitude 1. So right now it's of length 3, and I want it to be of length 1. So what I need to do is rescale this vector down by a factor of 1/3. So I'm going to write v here. And what we do when we're trying to indicate that a vector is a unit vector, the way that we indicate it's a vector is by putting that little like arrow on the top of it. And then the way that we indicate it's a unit vector is by putting a little hat on it. So if you see like f, if f was a vector and they put that hat on top of it, or if n was a vector and they put that little hat on top of it, what they mean is it's a unit vector. Okay, so what this is going to be is 1/3 of the vector v. Okay, now how do you rescale a vector? What's the algebra? All you need to do is just like that. You're just going to take all the coordinates and multiply them by that scalar. So this is going to be -2/3, 1/3, 2/3. Okay. And I encourage you to just pause the video and take a minute here and actually calculate the magnitude of this vector. If I did it right, you should get 1. Really common question here as well. Oftentimes we're in a situation where we have a vector and we don't want to change the direction, but we do want it to have some different magnitude. So in this example, I want a vector that's in the same direction as v, but I want it to have magnitude 10. So my method for doing this is the first thing that I'm going to do is turn v into a unit vector. So we already did that. So that's -2/3, 1/3, 2/3. So now I've got a vector that's length 1. And what I really want to do is have it have length 10. So it's real easy to scale something from length 1 up into length 10. You just rescale it by a factor of 10. So now 10 times v hat is going to be, so I'm just going to multiply all of these by 10. So what is that going to be? -20/3, 10/3, 20/3. So I've done it. I found a new vector that points in the same direction as v, but now it has magnitude 10. I should put down the abstract symbols for unit vectors. So what you do, the way that you produce a unit vector is you take your original vector and you rescale it by 1 over the magnitude. So you might see these symbols in a textbook that's referring to a unit vector. And sometimes for shorthand, they're also going to write it this way. They'll just put that magnitude in the denominator. And what they mean, so from now on, when you see these symbols here, you're just going to think, oh, that's a unit vector. One more thing is we don't call them numbers anymore now that we're using vectors as our basic objects in math. We really want to drive home the point that the job of numbers in this context is to rescale vectors. So we don't call them numbers or constants anymore. We call them scalars. Because that's the thing that they do is they denote changing the size of something. So these are the properties of vector operations. These are very important properties, so I encourage you to take a minute, pause the video and go over these. They should be very familiar to you. A lot of times we want to use words like associative or distributive, or maybe one like this. You can see that looks like an additive inverse property to me. This looks like a multiplicative identity property to me. So you should really be familiar with these things. I also want to talk about basis vectors. So basis vectors are kind of very basic objects that we use to build all of the other vectors out of. So they have names. They call it I hat, j hat, and k hat. So the meaning of I hat is the vector 1, 0, 0. The meaning of j hat is the vector 0, 1, 0. And the meaning of k hat is the vector 0, 0, 1. So they're unit vectors, and the I points down the x-axis, and j points down the y-axis, and k points up the z-axis. I don't know why I was saying down. I guess they point up the x-axis in the positive x direction. just a quick food for thought here, you'll notice that these vectors are building blocks for three-dimensional space, and I just want you to observe that there are, in fact, three of them. Okay, so a lot of times you'll see this notation, and I'll use this notation as well. So let's just check really fast that the vector 2, 3, 5 is equal to 2i plus 3j plus 5k. So these are kind of two ways to look at the same vector. One of them here is in component form. And then one of them here on this side is kind of built from these basic vectors here. And I do want to just check that these two things are equal to each other. So let's plug everything in on the right-hand side and see if we do get the left-hand side. So this is 2 times 1, 0, 0, plus 3 times 0, 1, 0, plus 5 times 0, 0, 1. Okay, so how do you multiply scalars and vectors? You just take that 2 and you multiply it by all the components. So this is going to be 2, 0, 0. This one is going to be 0, 3, 0. And then this one is going to be 0, 0, 5. All right, now I have three vectors added together. So how do you add vectors together? You just add the x's and you add the y's and you add the z's. So this is going to be 2 plus 0 plus 0, so I get 2, right? And then 0 plus 3 plus 0 is going to be 3, and then 0 plus 0 plus 5 is going to be 5. So you can see that we do actually have the right thing. So both of these are completely valid ways of writing a vector. A lot of times you'll see this is more kind of a math culture thing, and that's kind of more of a physics culture thing. So be comfortable. I don't think it's a big deal. Be comfortable looking at it in both ways and seeing that those two things are the same thing.